Recording. Okay, good morning, everybody. I did send out a quick note yesterday. I don't have anything new for us to discuss apart from the continuing the proposal for the New Frontiers proposal. I think if you guys were on the last call, I'm not sure. I think it was this call when we got notified that I got an email in from Oak Ridge National Labs, the procurement department, that the RFP, the final RFP, is on hold at the moment. And after chatting to some other people, I heard a rumor it was a continuing resolution, so it's usual government stuff, this delaying it. So it seems like it's still going to come out. It's just it's on hold until I guess whatever the blockage is cleared. So the good news there is it buys us a bit of time. The bad news is that, you know, when you don't have a deadline, things drift. But I was hoping that we can continue to make progress. So I wouldn't mind. Well, maybe. Obviously, we've been touching on this universal interconnect idea of the fact of, if we look at the way the world is gone or is transitioned, we've got many bus standards, many devices, and which arguably are obviously different at the protocol level. But when it comes to the transceiver level, they're becoming, you know, over the last decade, they've merged closer and closer together. And I guess the fundamental difference is that we see now is as we said, is the ultimate speed. Everyone's in the multi-tens of gigs, but with Ethernet, I guess in InfiniBand pushing the hundreds to 224 now. And then we've got the optics. We've had the big cages forever, obviously, again, but the optics have traditionally only been Ethernet or InfiniBand based for the fabrics, whereas now we're seeing the introduction of PCI fabrics. And if you've been following the PCI fabric interconnect, they've been adopting, well, they brought in the CDFP, which was a standard, which I think Molex and TE did one of the collaborations, whatever the name of the collaboration is for these standards, and came up with CDFP, which is now the official PCI by 16 interconnect on in PCI SIG. But that said, as the industry seems to have been percolating in a different direction, I think I've seen a couple of companies come up with QSFP-DD, PCI CXL interconnects, with the by 8 lanes, and because it looks like the by 8 lanes may be a little bit more preferred for the communication rather than by 16, and I think it's difficult to bifurcate the CDFP, and maybe even CDFP is working on a by 16 bifurcation. But you can see there's a lot going on, and then we've got others like NVLink and Infinity Fabric and UPI. And then you've got startups with their own proprietary buses as well. And so it sort of feels, you know, at the end of the day, if we are going to go to this universal module that we're trying to do with HPCM, is there a way to get to a mechanical and electrical level where we have this Lego brick pluggability and the decision of what protocol travels over it is decided at the software firmware level at power uptime, you know, so it's dictated by the silicon that's put on these modules. So that's sort of the vision and the passion of what I'm trying to do here. Obviously, we all know that historically things have gone in different directions, like the impedance is the big one, I guess, which I guess in general, we're saying, looks like we've got the impedance, you know, solved. So we've already discussed all of these. So I guess the first thing is, and the fact of active cables and miniaturization. We see the whole world miniaturizing. We get thermal densities going up into the kilowatt regions in these tiny modules. If you think about a kilowatt for a processor, in the optical in the electrical and optical active interconnect, we're at this QSFP-DD, and now we're moving to OSFP because we can't cool it in a QSFP. And it's like, but if you look at the miniaturization of the optics with silicon photonics and the miniaturization of even the electronics going into these things, they could fit in. All of this technology can fit inside these smaller near package interconnects that we've been doing, and we're seeing cables everywhere. So again, with a bit of conduction cooling being brought into this, and the power's dropping, or well, not dropping per se, but the speed's getting up in lower energy per bit on some of these IOs. Could we have a more of a direct water cooled solution for these active cables? So anyway, full story is really, can we get to this universal interconnect? And I guess I think that's a big motivation here, that even as a standalone project for an investigation from a DOE perspective, or these HPC machines, because one year the machine is AMD talking Infinity Fabric, and the next year it's NVIDIA talking NVLink. Hopefully we'll have one day talking CXL, and in reality, we're going to have all of them in some systems where you're mixing and matching to different ratios. And so it's going to be an absolute mess if we don't try to bring some universal interconnect. So I think actually just stand alone, we have a tremendous opportunity here. And I think it'd be something that the government might be willing to fund in this proposal. So and I'm not saying anything new, but we've got this time now that the RFP is on hold. We don't know how long for, whether it'll be released in a couple of weeks or a couple of months. But I guess one thing that does happen in these OCP work groups is we have a little bit of time of people that are willing to attend this and put some man effort into this, or person effort into this, should I say. Then we have the ability to at least create a spec, and I guess that's what OCP does quite well. So we could start working on a base spec here, and if we actually have a spec of whatever form, I mean, if we could get to a full spec pretty quickly, then we could put that into this RFP proposal, and we know exactly what we're going away to make if the government gives us funding. So it's much more clear as to the solution we're proposing. So I guess my question there is I guess we have a subset of companies on this call, the people that attend and the people that can participate. How do you guys feel? You're from, I think that we've got 4 different interconnect companies on here. How do you guys feel about maybe trying to get going on actually writing a spec for this that we can then put into the proposal, or reference in the proposal for turning the spec into a reality?
I think probably the first part of this, looking at calling something universal, would be defining where it would fit. Obviously, we have IO stuff, and we have internal stuff, and we have power stuff, and we have, super high speed stuff, and we have grounds and power, and there are an assortment of mixed hybrid interconnects that are out there. But does it need to be, is this a pluggable, is this a permanent install? Is this a connector to ease manufacturing complexity, such as a chip carrier that connects a incredibly complex device onto the surface of a board? Or is this something that's got to carry a giant bundle of uh, high-speed data cables? So to make
Yeah. So, okay, now good. So I guess, Howard, I think you've been on a couple of times, so you may have missed out on some of the detail. Happy to let me just share our inaugural meeting slides, and can you see this first slide?
yeah, there's
Okay.
our chip carrier and there's our
So yeah, so this is the module standard. So the module standard is one, and this is the interconnect of which these 16 central connectors are E3, E3.S, where they're 4C and 4C plus TA102 connectors. So that's pretty standard, apart from some mechanical changes to this to give compatibility with the cooling and getting rid of through hole features. But this is these ones on the outside we've got 8 what we call topology interconnects, and these are the ones that we're talking about converting into our own universal interconnect. Okay, and so what this is today, in fact, this diagram is the MCIO PCI 6 CIO 8-lane version. So I guess, I mean, it's a good question. You know, universal is a strong word. If you can't put 128 lanes down to 1 lane in a universal connector. So I guess we have made a little bit of a decision in the discussion, at least, that 8 lanes seems like a sweet spot. And in this interconnect spec, when we talk about the topology, basically this is the definitions that we on the left. On the right are connector implementations that seem to be fairly current, where like I said, MCIO is PCI SIG, it's a paddle card approach. Samtec have their accelerate, where it's a direct wire to pin. There is no paddle card, and that's for the 112 gig plus. And Molex have a similar but different approach to a direct wire to pin interconnect called the near stack. So we've got these different approaches for these differing use cases. And so, but what we're saying on the left is we really want to try and make something universal. So we would like it to be protocol agnostic. It can talk at any of these things. We have some impedance considerations to get over here in terms of, you know, trying to normalize like we have to 92 ohms, but what's the impact of not being as close to the correct impedance as possible if you're trying to go all the way up to 224 gigs. So we've got this by 8, we're saying 112. We're saying it would be nice to go to 224, but hey, maybe we can go to 224, and maybe passive doesn't make sense if we went for a paddle card approach, and therefore it would only be for active cables that we get to 224, but the interconnect can keep up without too much crosstalk, etc. Then on the sideband side of things, we could reinvent that to be, instead of this bag full of signals, we could try and simplify it to a differential pair, differential pairs for clocks, and maybe the only static signal is a cable present signal that just knows that there's something plugged in. And then on the active cables, obviously we've got to think about powering the active devices. So we need power pins. I've said approximately 5 watts, but you know, so we could say in the 5 to 10 watt region, where and just said 12 volt power pins. It doesn't have to be 12 volt power pins. It could be less, but then we need more current per pin, or it could be more, you know, so you need more pins. Or I wouldn't propose we go any higher than 12 volts personally, but and then we would need a paddle card of sorts to support some active components. So when I looked at that totaled 66 pins. And I just did a quick swag of the interconnect, you know, what it would look like in a 2-row interconnect. And so that's that, you know, so this is what we're, you know, we're trying to, can we cover all these bases with one design, and optical as well. And then, sorry to bore everybody else, but I don't have my app running. I have to. I can open up the model just to, oh, hang on a minute. No, I can't. I need to open up on. So I need to transfer. I got two different versions of the software. Anyway, don't believe. Yeah, the model I was playing with was all right. I can't show the model, but what we were doing is we were playing with the MCIO interconnect and the Samtec one, in terms of how could you attach a paddle card to these direct cable to pin. So we had some ideas there, and I think you might have been present for those actually. So anyway, so does that help define what we mean by universal, and or do you think that's too constraining what we're saying, or too or not constrained enough?
No, oh, am I alive here? Yeah.
Yeah.
You hear me typing away here. No, that focuses things a whole lot more. And I don't see there's any reason not to call it universal. Eventually it'll get its own name. But the goal meaning being that there's a combined solution that solves a group of problems, but maybe built in a level of flexibility that that you can have not only power and signal, but a variety of signals as well, depending upon how you configure the intermediability. So yeah, I have no issue with universal, but realizing universal is not all encompassing.
Right.
So yeah.
Yeah. I guess you got to put some limit on it. So I guess the number of lanes. The other thing that we were also with the optics, we were trying to say, could we include co-packaged optics? So if we put some, again, the USB, the old-fashioned USB standard was electrical, but way back, Intel did propose a couple of optical holes at the back of the connector where you could put a passive optical cable for a USB in, and you know, so it would be the same receptacle, but you wouldn't need the electrical pins anymore. So you could almost put dual compatibility in that. You just have a passive optical cable, or you have electrical, or you could have one or the other, and not both. So in the co-packaged optics world, we were talking about, and we were using Avicenna as the example, but because they gave me a little 3D model of the size of their optical interconnect, where they were 2 terabits per 1 terabit for transmit, 1 terabit for receive, and we could fit 4 of those into the footprint of, you know, co-packaged wise into the footprint of one of these connectors. So we could get a terabyte per second per connector of optics, where you know, you wouldn't need any of the electrical interconnect if it was a co-packaged optics approach. So it would be more of the same mechanical body and cable assembly that you would have. So you're, you know, footprint wise, you're taking up the same sort of real estate on the module, and you know, it's you have that potential. Now, obviously, once you choose an approach, you don't use the electrical one. So why bother soldering down an electrical connector when you can just put down a mechanical optical connector, which might be cheaper? And so, yeah, you might have variants, but they all fit within this universal standard. So from a mechanical latching and all the rest of it perspective, they're pretty much identical. It's just obviously the guts of the connectors are slightly different for the pure optical versus the electrical.
Hey, Aaron. I keep hearing you go around the pedal card or without the pedal card design. So I think I'm kind of getting confused now because now we are doing the universal solution, right? And all the way up to optical
Right.
interface. So I thought
Recording in progress.
Hang on. Sorry, guys. Okay. Okay, can you still hear me?
yeah, I think now is it's good.
Okay. Yeah, sorry, I was just bringing up the model again here. So let me stop sharing on this side, and let me share on this side. Okay, so I just brought this back up. So can we see this? So yeah.
So what I'm going to say is, you know, for the optical, you have to have a pedal card, right? So I don't know what's your judgment on when you're talking about that slides and you're going around the pedal card argument. So it seems you prefer like the no pedal card, but obviously if you do universal connect interface for optical, seems pedal cards is a must, right?
So there's obviously 4 different cables that we could do if I've got them all right. One is passive, just copper cables, no active parts at all. The second is an active electrical, where you need a paddle card. The third is an active optical, where you need a paddle card. And the fourth is co-packaged optics, where you'd really only need a body, a mechanical body for optical fiber alignment, when you mount these fibers in. Does that make sense?
Yeah, so if from what you are talking about, I just feel you are talking about the argument on the pedal card versus the no pedal card. You are only talking about the passive solution.
Yes. So on the passive, so I guess my experience. My experience is I was working. I worked for Molex, and I was more of an observer of the technology progression of the performance of cables. Was that the paddle card got in the way of performance, especially 100 gig and going up to 224. And so for the best signal integrity channel, a passive cable is better to be soldered directly onto the pins. And obviously, the traditional paddle, and arguably, I guess that was what we were discussing, right? And we said that a paddle card would still be okay, but you'll probably get some signal integrity impact. So I was just wondering about the viability of any passive copper at 224. So that was the only reason for favoring a passive cable, a direct to pin approach. Otherwise, we could do a paddle card for all, which would be this one, this is the MCIO that we were talking about. So therefore, the passive paddle, the passive approach is you just solder the wires onto the paddle card, and the paddle card then connects to the pins. So yes, we can do this. I guess with the Avicenna implementation, the optics is mounted on the side of the paddle card, and then you have to bend the fiber, and you have a certain bend radius that you can do because the optics comes out the top. But I guess the optics can also come out the side if it's silicon photonics. They can come out the top or the side. So fair point. If they came out the side, then this paddle card would work. What I was showing here is this is the Samtex Direct cable connect, and I was suggesting we could put a paddle card circuit board onto the pins like this for an active cable, and this would be good for a very clean vertical launch off of this board here. So I guess the only thing that this felt not right was we seem to be going through too many 90-degree bends. You know, you've got the motherboard or the board where the connector is mounted. You've got to go for a right angle to get to this, and then you're on a paddle cord this vertical, and then you've got to go vertical out and then right angle again to get the fiber out. So you know, so suddenly this connector has got quite large because of the launch of the fiber cable compared to a paddle card mounted on something like this. That was does that make sense as to what my thought process was? I'm not saying it's correct. I'm just saying, does that make sense? Do you see what I'm...
Yeah, Alan, yeah, I understand on the optical side. Yeah, I was trying to think about when you talk about the slides about the pedal card thing. Yeah. So, and actually on the MCIO, right? We are also, yeah, for the passive, basically for the passive solution, it's not always like PCB pedal card is being used. Depends on the performance needed. Yeah.
Oh, isn't it? Oh, okay.
Yeah. So yeah, so that is a little bit different, I think. Yeah. From the standard.
So for a passive, it isn't. So how does it work with because an MCIO is a paddle card approach, right? For passive, no?
Yeah, so I mean that it's not always the PCB pedal card. So I think you assume the PCB pedal card that has more loss, right? And
oh, you're saying it's a different material, so you don't have the
different materials. Yeah.
Okay, all right, fair enough.
Yeah.
That's me, but not being out of date. Okay.
Yeah, just a little bit.
So I mean, to be honest, we started with MCIO. If we can make MCIO work, then great. Obviously, when we start writing this spec, we have to deal with how would these things launch. Like this launch here, I don't know if this is the minimum bend radius. I mean, this is what Avicenna have for their model, right? If you look at other silicon photonics, they can launch from the top. Apparently, theoretically, there's no reason that they couldn't launch from the bottom, which is quite interesting, but nobody does. Or they can launch from the side, like if they're the V grooves in the silicon photonics, where they mount the fiber. So this particular example would benefit from a side launch where the fibers literally can come straight out the top in planar with the paddle card itself. So that would be good. So I guess that doesn't rule it out. We would need another discussion with Avicenna in terms of, or we would need to say that, okay, I mean, obviously I've put it on this side, maybe what I could do is possibly, what you could do is you could do it that side, I guess. you're still overextending the body of the current connector, but
Yeah, that's a little bit difficult on their side is the latch is there, right? So
oh, you've got the latch on
yeah,
that side as well, right? Well, plus
yeah.
we
So
need, plus we need
unless
the thermal
we
connection as well, right? We need the we do need to be on the side of the thermal because the active components, and that's so yeah. This optical. So we also something we're not considering here is we need to thermally cool these actives.
oh, Alan, seems we
Yeah, sorry.
we
My iPad just ran out of power. I was sharing. So anyway, yeah, we've got the thermal aspect to consider as well, obviously, which is another. So on
yeah, I think the question will be the how big the distance the gap, right, between that cable connector to the next module.
yeah,
So whether we have enough space to squeeze in that optical one, yeah.
That's a good point. Yeah, so actually when this particular design, there is actually quite a big chunk of space here. I mean, so technically, but again, we need to think about, we need to get a good thermal path as well as an optical launch. This is why I favored an optical launch out of the bottom of a device rather than at the top, but no photonic company does it that way today. Although, like I said, I was told by one of the professors that there's no reason the optics can't come out the bottom, or the other side of the silicon to the electrical. And this is where I was talking about like if you can launch the optics, you could have the idea here. If I go back to this diagram, the idea here is your co-packaged optics could be mounted on the top here with the electrical signals going between chiplets on this top layer, and a hole could be drilled in the board that would then the light would be transmitted down through to the connector. So there would be no, it would still be a clean printed circuit board to mount the connector, but the light would come through from the top through the hole in the board. And then the photonic chips would have a clear surface for a conductive cooling, or either a liquid cooling over the top of them, or some sort of gap pad or conductive cooling to the heatsink above, if this was a heatsink design. So optics out the bottom, the novelty of this design is you've got the wet side on the top and a dry side, an interconnect side on the bottom. You've got the 3D area for a lot of interconnect, right? And you can imagine if you had co-packaged optics all around this device, you could have I guess as we progress, it's like version 1. As we go to a full-on silicon photonic co-packaged optics world, then maybe we change the format of these. But equally, these modules are like Lego bricks. So again, that as long as the cables are common, or the interconnect cables are common, you can mix and match different module types. So anyway, so that's my thinking. But again, sadly, the photonics world at the moment doesn't agree with. And this is where the photonics world has been living in a box from the bottom up. And there is a desire, they need to think from the systems down. And if you look at the Ayar Labs implementation of their photonics with Intel, they've got this wonderful PCI card with an Intel FPGA and some others, but the manufacturability of that with these fibers keep breaking, and the fact that they've got these fibers coming in, and then you've got to get a big heat sink on top, and then you've got liquid issues. It just makes little sense. Everything's not thought about from a system level perspective, and that's what we're trying to say here is, so if I could persuade Ayar Labs to bring their optics out the bottom, then this would work, right? But that's the problem with working across the silos, is you need everybody to work together to make the ideal solution going forward, whereas evolutionary, everybody just tries to fit with what they've got rather than work on what would be ideal. Yeah, so I guess, yeah, well, so going back to that model, that depending if I guess my view is optics out of the bottom would give us the ability to cool an active optical cable on one side to the conduction cooling on the other side would be the optical launch, and maybe you could actually get a tighter bend on the optical launch if it actually was coming through from the other side of the board, but we'd still need a bend, so we'd need to follow some sort of minimum bend radius which the optical fibers can do, if that makes sense.
Yeah, Aiden, this is Jason. I didn't start from the first meeting, but just jump in between. And from the system architectural viewpoint, one critical question is I read through the proposal. The one fundamental question is, what's the protocol will run among this module and inside the module, because that's well related to the reference impedance things. So
yeah, exactly. So the whole idea is we don't know what the protocol is until we put somebody's device down. So if we put an NVIDIA chip here, it'll be NVLink. If we put an AMD, it'd be InfiniBand, or we could have PCI CXL, or we could have Ethernet, or we could have a mix of all of the above. So that's the whole idea of a universal interconnect, is that we can be protocol agnostic in one mechanical electrical design.
Yeah, but the question is, if one module is Ethernet, the other module is the PCIe, but they need a communication in between. So whatever there is one node area, they need to do the conversion.
Right. So good question, good point. The idea is that you would be able to interconnect them mechanically and electrically, but at no time the system management of the system in the modules would actually, before turning anything on, it would interrogate all the modules. They'd all communicate, and they would identify the interconnects, and they would say, we got a problem here. We've got CXL trying to talk to Ethernet. And you'd get a failure report saying this interconnect is an illegal interconnect. It needs sorting. Or some of them, like Infinity Fabric, can have a dual mode where it can be PCIe or Infinity Fabric. So you could switch into compatibility mode. So you would tell them to go into compatibility mode. So
but typically this one need a 5 chip. Okay, they can convert not just a signal, is a protocol. Okay, so the packet structure is totally different. Okay, so I think look at the server, and when they get the outside world, with the Ethernet, they go through the NICA and they have the 5 chip convert the PCIe.
Yeah. So there's a couple of ways we can do that. First of all, we've got so many billions of transistors now. You'll see a lot of people are sucking the Ethernet PHY, if they want some Ethernet, into the silicon. And we don't need network chips. In fact, our network cards are a waste of time, in my view, unless they're doing something, if they're intelligent. But anyway, we'll get on the philosophy of the architecture. I mean, this has also been architected thinking about from the system architecture perspective, but ultimately, your interconnect, and by the way, we're in this sort of Cambrian explosion of interconnect. If you think of all these damn proprietary standards, as well as CXL and all the rest of it coming along, so I don't see it changing anytime soon either. Even startups have their own point to point between their devices that are just talk their particular protocol. So so firstly, there will be no chips. Obviously, you might be able to put a retimer in here so that you can transmit over a longer electrical cable, so an electrical retimer. And then with the chiplet world, if you had pluggable chiplets, which is something I've been talking about for a long time, but isn't really getting people's attention, is you could talk one little chiplet language at around 1 to 2 picojoules per bit on the main processor, and then an active cable could convert it from the chiplet bus standard, call it UCIe for sake of argument, to CXL or Ethernet or whatever else. And so, yes, you could actually put an entire NIC card at a low energy or, retimer level into the active cable. So your active cable could actually do a protocol conversion as well at some particular point. Now that I didn't really want to pollute things, but potentially part of bringing all this so close together is this module. Is this chip is really pretty close to these. So I did an analysis with IBM where we're in about a 5 to 10 dB loss range. In fact, more closer to 5 if we got rid of the big package and just made the entire module a package. And that would give us in the region of 1 to 2 picojoules per bit we could get down to for this pluggable interconnect between these two. But in that sense, you'd always need an active cable where you would just add the extra reach wherever you wanted to reach another foot or another 10 meters. Your active cable would do that extra reach. And if at the same time you knew that at the other end, you could make a whole bunch of cables that talked different protocols and converted between you. So you'd effectively be putting a NIC card, if you like, into the active cable with this miniaturization. And yeah, so that's the possibilities become quite significant if you start to think along those lines. And ultimately, we're migrating towards a co-packaged optics. And once we sort that out once and for all, depending on the cost, at certain speeds, everything will just be co-packaged optics. But we're trying to say this world is going to be in a transitionary mode now from today onwards. And we need to be able to live in both worlds and start to bridge the gap rather than have a binary change at some point.
Yeah, I think if we call universal, but let's look at many kinds of the protocol coming. And if we don't have the defined in this big board and the module, and then they will later on will very messy. I can say that. Okay. So my idea is suppose we need to define what's the main protocol in for the communication between module to module, and inside each big module there are several small module plug in, and they may have the same protocol. But if you have the different protocol plug in, suppose for example like the NIC card, and you have the all different riser card, you have different protocol. You supposed to convert to the same protocol in the
No, so that goes completely against what I'm trying to do here. So we're just trying to define that we have one connector and cable that can connect all protocols.
Yeah, that's no problem. But the point is just not the connector, no problem. But behind that connector, the plug area, you need to do the conversion to make sure on module board they have the same protocol. Otherwise, you bring different protocol in.
No. So like I said, the system management, the common piece on this is this sideband. So we have this tunneling. I've called it LTPI, but whatever this is its own serial link, and this is the only one that is the defined protocol. A bit like we've been using I2C for 40 years or 50 years. It's saying
Yeah.
this is a gigabit or whatever the speed of this is our communication. So before power on of the high speed lanes, this is the one that actually says, this module is talking NVLink, and the other one says, my module is talking CXL, and they're connected together. And then this communication says, that's not going to work. I'm not turning on, or other mitigating actions. Like it doesn't turn the link on, it turns the system on, but that link doesn't come up. But then that's part of the system management of the overall machine of hundreds of these modules or thousands of these modules. So it's a negotiation that goes on before we. So therefore, this connector again is the same no matter what protocol we put across it. That's the idea. That's what we mean by universal.
Yeah.
And not that it can't become specific, but ultimately, the protocol is dictated by the chip that is put down on the main module and the IOs that are connected to these connectors. That's the idea anyway.
So the question is because for example, you can detect no problem. Okay, your base is PCIe, but you detect the plug-in is Ethernet, the protocol. Okay, then they still need to plug in, but how can you convert the Ethernet to the PCIe?
You don't convert, you just don't work. If somebody wires an Ethernet to a PCIe, it won't work.
So this means this module, you, for example, is run Ethernet, then whatever you need to plug in Ethernet. Is that right?
No, I mean, look, so if this, let me give you a couple of examples. For example, Infabrica are a new switch company, and they're a CXL switch company. But what they've got is they've got a certain number of lanes are CXL, and a certain other number of lanes on the same switch are Ethernet. So if you imagine they're like multiple NIC cards in a single switch. And so depending on that, you would decide which ones of these you want to be Ethernet. I mean, the way I've been proposing for their particular chip is that all of these buses, these are PCI, right? So this interconnect here is TA1002, the E3S modules. They are basically CXL PCI. So to your point, these are protocol specific in terms of how they exist today. And so that's fair enough. But we're talking about these topology ones, the ones that connect modules together that are topology agnostic. So if we made the decision that this Infabrica switch was going to be Ethernet on these, then that would be it. And then if you went to a so if you take Habana Networks, for example, their chip is entirely Ethernet. So therefore we could connect directly to them. If you had basically, if you had an NVIDIA H100 module, NVIDIA only talks NVLink. So we couldn't plug the NVIDIA NVLink topology to this, but it does have a PCI bus on it, which is the main host connection bus. So we could put a cable between one of these TA1002s in the CXL switch and the H100, and we would have a successful connection. Then the NV links could only talk to the NV links. And if this was an Infabrica switch, it could convert NVIDIA's PCI connection to an Ethernet, because going through the switch. So we would operate like a NIC with that particular setup. So that's the idea. Now we do also have capability in here that you could plug in a NIC 3.0 from OCP. We'd have to do some mechanical changes to the NIC 3.0 standard to make it fit. But basically, we could plug in a NIC 3.0 if you wanted to convert this PCIe into an Ethernet as well. So do you get the idea? Again, we're thinking forward for everything here is the way we're thinking.
So when you talk about this, so you mean this switch, for example, switch chip, they include some kind of file chip. They can do the conversion. Is that right? It's from the Ethernet to the.
Or you know, I can talk about other companies. I can't, without mentioning names, I know a number of accelerator. Well, say an FPGA. An FPGA, its transceivers can talk Ethernet, PCI, Infinity Fabric, OpenCAPI, NVLink. An FPGA can talk anything. So it would, an FPGA is a perfect match for a universal interconnect because the FPGA can be configured to talk any protocol. So if you have a protocol problem, you stick an FPGA in the middle and it can convert any protocol to any protocol, provided it's got the IP to do it and the license. But NVIDIA won't give Xilinx their IP for an NVLink port. But assuming, you know, the FPGA could be your universal interconnect to convert any protocol to any other protocol.
Yeah, I agree. That's to the FPGA. But for future application, everyone kind of need this kind of FPGA chip. That's where cost will be high.
Well,
right?
no, arguably, you know, if I'm the government, I might say, I particularly like NVIDIA's GPU with AMD's CPU or AMD's FPGA, and I want to mix and match them, and I want to put a switch. I don't want a leaf in spine. I don't want a top switch. I want an everywhere switch. And I want to wire these things up, or I want to wire a big fat pipe directly between two modules, a bit like Grace Hopper. I can do any and all of these things with this approach. Ultimately, we would like to believe that we will converge as an industry. Instead of all of these different fabrics, we will converge to one fabric that is a maximum bandwidth, zero latency, zero power. You know, all the ideal is where we want to go, right?
That means that we need to have this kind of universal chip. They can handle that. Okay.
Right. So this is basically the first baby step to say, what can we do if we look forward to where the world could be, and we are all talking one beautiful fabric that has all the attributes of all the others, then great, we've got this, but we live in a world with an exploding growth of fabrics. And albeit it's great for you connector companies because we got to buy a million different converting cables. You know, it's no good for the industry in terms of scaling this. And allowing for democratization in across these incumbents, which is at the moment, you know, it's, you know, if the government's buying a machine, it's either it has to be 100% NVIDIA or 100% AMD or 100% Intel is the way it's looking right now.
Yeah.
And with CXL, you know, CXL, I've done a presentation on this at the moment, is a poor man's NVLink or a poor man's Infinity Fabric. And these guys that have their proprietary buses they won't tell you this in public, but they don't want CXL to be that much of a success because they like the advantage of their own proprietary fabric. And so we need to be able to interconnect their fabrics when it's their devices talking to their devices, but we need to be able to talk any other protocol depending on the needs of the application and the I/O availability of the different accelerators, etc.
Yeah, from the application is a very kind of flexible, okay. But in the hardware, maybe for any module you plug in, suppose each module need to come with this chip. Otherwise, because you will plug in unknown word, right? And for the fully communication, then they need to have this kind of the capability to determine which kind of protocol the other side will provide and to make sure the communication. So every module need to come with this kind of chip. Definitely.
Each module, the system management that's another work group where we meet on Wednesdays. But that is one of the key topics is the system management chip that's on here.
Okay, they own that. Okay, I agree.
And the system management chip will be universal to every single module. and we'll be the thing that negotiating, and it will work with the DCSCM module somewhere, one root of trust module, which then connects all the modules together and does this negotiation and telemetry, and everything is actually managed from that. Yeah, so including, yeah, can interconnects that have been connected talk to each other or not?
Okay. Yeah. Okay.
So you certainly there's many ways to get it wrong by having this universal interconnect, but we need intelligence built in to identify that and stop it from happening, or get it rectified if it does happen.
Okay, so that's maybe the meaning of we call intelligent universal. Okay.
Yeah. So I mean, that's where this sideband, this tunneling, this basically, this is going to be the. I also often call it the control plane. It's like the management control plane going on. That's just controlling, and so this does need to be the common everywhere, and we're using FPGA, something called Libra BMC, which is a completely open sourced hardware on an FPGA with open source software, the OpenBMC, etc., and all the layers above. And that layer that doesn't exist today will be a layer that says the protocols need to match the either end of a particular interconnect.
Okay. Yeah. Thanks. Yeah. Got your idea. Is this
Okay. No. It's good to discuss it. Thanks for the questions. It's good to make sure we all understand what we're trying to achieve. And I realize we have some hurdles like impedance, discontinuities, and speeds, and and so that's what we're discussing. I guess what we can, so I guess in putting a spec together, if we can get the spec going, some of these more thorny problems of, well, how do we manage a corner turn of a fiber in the connector and not make the connector blow up in size too much, or do we only have rear connected optics, and so therefore we ask the industry, we need this type of implementation, and it might be, again, that might be a thing that the government can say this makes sense, and we're happy to fund somebody to do a silicon photonics with the optics out the bottom rather than out the top or side, something like that. So anyway, so I think if we get going on the spec, if we can get going on the spec, then we'll be able to pull this together a bit more, and the problems will pop up, and either we'll be able to solve them or we won't, I guess.
Okay. Yeah, thanks. Yeah.
Makes sense. All right, guys. Well, I've run past the hour, but good discussion. And again, if let me know. I mean, if we want to start to create a separate dedicated spec for this that we can potentially publish with OCP, that might be a good thing to do.
Okay.
Okay. Well, thanks very much, and speak to you next time.
Okay, thank you. Bye.
Okay. Thank you. Bye.